fingerprint of a compound from an infrared spectrum. It can be used for qualitative and quantitative analysis. It can be used for organic and inorganic samples. We get the complete picture of the structure, as I said, and the composition of a mixture. If it is a mixture of compounds, we get the composition, we get the functional groups in the molecule. It is exactly like a fingerprint for a human being. When we go to the airport and other places, when we do the biometrics, when we press our fingerprint, the system will get the complete history of us. Everything about us will be displayed on the screen. Similarly, if we do an FTIR spectrum or spectroscopy of a sample, we get a complete picture of that sample, what it is and what all things are there in the compound. This is an example of a compound, any compound, chemical compound, or it is whatever it is a compound, and you can see there are molecules, there are vibrating atoms, and the red ball is the infrared light that is passing through the sample. What happens is that you can see these are vibrating at a particular frequency. It is like a simple harmonic oscillator. It is vibrating at a particular frequency. So this red ball, which is the infrared radiation, it carries a range of frequencies. When it passes through the sample, some of them will be absorbed, and we can see the other end, which is transmitted, the light which is transmitted at the other end will be lacking in that particular frequency, and from or by studying that transmitted light, we get the complete picture of this compound. Now let me take you through the timeline. Briefly, I'll take you through the timeline of infrared spectroscopy, how it started. So in the beginning, like first we have to discover the infrared radiation, right? In 1800, a scientist named Sir William Herschel, he was studying the temperature of the colors, different colors of the white light by using a prism. He was making like the VIBGYOR, you know, the violet, indigo, blue, green. He was studying the temperature of all the colors by splitting the white light into the different colors. When he placed the thermometer beyond the red light, he saw that beyond the red light, the temperature was the highest. And that was a key discovery. That was when he discovered, or he understood, that there was something beyond the red light, which is invisible to our human eyes, but there it emits some high heat. That is how the infrared light was discovered. Infrared means beyond the red light. And after that, there was another invention, that is an interferometer, which was invented by Albert Michelson in 1880s. See, the IR light was discovered in 1800 and the interferometer was discovered in 1880s. But still, the scientists knew the infrared light is there, but they didn't know how to make it into practice. Then, as usual, they started the experiments. They began to pass this light through samples, gases, liquids, solids. But after certain experiments, they noticed that some of the wave, it was in the beginning. So it was just the starting. They understood that some of the lights were missing. That was the first clue that they got. Then after some various experiments, they understood that it is unique. Like no two compounds will have the same IR spectra. It is unique for that compound. Then it was a key breakthrough. Then they understood, wow, why can't we use it as a molecular fingerprint for a compound? Then it was the dispersive infrared era. They manufactured a spectrophotometer, which was a dispersive one. It was formed in 1940s. But it was just the beginning. They used the prism or the grating as the monochromator. In the beginning, they could pass one wavelength at a time, not all of them together. But still, it was very effective. They used this prism or grating monochromator, and they could study the structure of the compound. But the drawback was it was very slow, it was less sensitive, and they required more samples. But later, then they understood they have to do something about it, and they tried to make use of the interferometer that was discovered in 1880s. In the beginning, why they couldn't use the interferometer, even though the interferometer existed, but the practical infrared FTIR, if it is used in an FTIR instrument, they required faster computers, sensitive detectors, or advanced optics. It was lacking at that time. Even though the interferometer was there, they lacked all the other essential things. So it took some time to develop a proper FTIR spectrophotometer. By 1949, the first FTIR spectrophotometer was made, and then later it was used for commercial use by 1960s, and there it used the Michelson interferometer. By 1966, the technology advanced. They used fast Fourier transform, and it was commercialized. This is the short history of FTIR spectroscopy. Now let's come back to the infrared light. Infrared light, I showed you, it lies between the visible light and the microwave region. So it has a wavelength longer than the visible light but shorter than the microwaves. And this infrared light is divided into three regions. It is not one region. For convenience, they divided it into three spectral regions: near IR, mid IR, and far IR. From the name itself, we know near IR is the one that is close to the visible region, and the far IR is the one that is away from the visible region, or we can say close to the microwave region. In the chart, you can see near IR, each of them has a particular wavelength, or in other words, we can express it in wave number, frequency, or it in hertz. We are focusing on the wave number because in FTIR spectroscopy, we mostly talk in terms of wave number, which is the inverse of wavelength, centimeter inverse. So as you can see, the near IR, mid IR, and far IR, most of the researchers are focusing on the mid IR region, which is from 4000 to 400 region. You know what's the reason? Because most of the important absorptions, like functional groups like OH, carbonyl group, alcohol, aldehyde, and hydride, these are confined to the mid-IR region. Most of the organic compounds, the absorption is high in the region, and most important bonds happen in this region. And one more thing is, it is strong and well-defined peaks happen in this region. So people are mostly focusing on the mid-IR region. Even though we have near IR and far IR, the focus is mainly on mid-IR region. Now, what is the principle and theory of FTIR? We know there is a source. From this picture, we can see there is a source of infrared light which passes through the sample. After passing through the sample, it carries the information about the sample, what the radiation, transmitted light pass carries the radiation through the detector, and then we can interpret the spectrum. In the image, we can see P0 is the incident light, which passes through that block, that is the sample, and P is the transmitted light. We all know Beer-Lambert's law. Beer-Lambert's law states that absorption is directly proportional to concentration and path length. So, when a sample is taken and a light is passed through it, the amount of light that is absorbed, it depends on the concentration of the sample that is present in the this thing, and the path length, how much area it is there. So we study the radiation coming out of the sample. In FTIR, we can represent the spectrum in two forms. It could be in percentage transmittance mode or absorbance mode. You know, absorbance, here mostly we give the result in percentage transmittance mode. If we see this radiation, it is written percentage transmittance is equal to P by P0, the intensity of transmitted light divided by the incident light into 100%. In the spectrum, it will be more clear. I'll take you to the spectrum and explain in a better way. So what is the theory? There is a source of light, the infrared light. Okay, the source could be a Nernst clover or silicon carbide. There are various sources of infrared light, or even a heated rod acts like a source of infrared radiation. A heated rod produces an infrared light. So it passes through the sample material. That is the first step. See, a source of light passes through the sample material. Then what happens there? Depending on the energy, it can trigger the vibration of a specific molecular bond. You can see how the molecules vibrate. Vibration means a change in the shape of the molecule. It could be stretching, bending, or internal rotation. There are various kinds of vibrational modes for a molecule. See, these are the most common molecular vibrations. First one is symmetric stretching. You can see it is a carbon. Okay, this is a water molecule. So it is, first one is symmetric stretching. Second one, we can see it is asymmetric stretching. Next is the bending vibration. First one is scissoring, like opening and closing of a scissor. then it is rocking. The third and the fourth are in plane vibrations. But the last two, you can see the wagging and the twisting, they are moving out of plane. So these are the most common vibrations. So when IR radiation passes through a sample, it will trigger this kind of vibration. And then what happens next? We know, I told you there will be some absorption, but all the lights are not, all the radiations are not absorbed. Absorption happens only if the frequency of IR radiation matches the natural vibrational frequency of the molecule. So this molecule, HCl, we can take as an example. It has two atoms. There is a bond, and according to Hooke's law, it acts like a spring. There will be a vibration, like a harmonic oscillator, but ideally, no bond is a simple harmonic oscillator. There will be a slight variation. It is unharmonic. So we can say, theoretically, we can say the frequency of this vibration is this equation 1 by 2 pi into root of k by m, which is derived from Hooke's law. We can see m is the reduced mass. It depends on the masses of two other atoms present in the molecule, H and Cl. We can see that the equation is m1 into m2 divided by m1 plus m2. So when the radiation passed through this, suppose this bond, when the radiation hit this molecule, it has a vibrational frequency as shown here. So if the IR radiation has the same vibrational frequency as this HCl molecule, there will be a vibrational transition from the ground state to the excited state, like this. You can see this is an oscillating bond. When the radiation matches the natural vibrational frequency of that bond, you can see the radiation hitting that sample. Then there will be a transition from the ground state to the first excited vibrational state. This is called the fundamental vibration. Ideally, for a simple harmonic oscillator, only this transition is allowed, ground to the first excited state. But our compound, it won't act like a simple harmonic oscillator. Because of that, there will be transition to the higher energy levels like E2, E3, and these, I will come back to that later. There will be, it is not fundamental, it will be integral multiples of the fundamental vibration. That is why we get a complex FTIR spectrum. And then all the wavelength that has passed through the sample is gone through the detector. And when you get the result, it will be a spectrum like this. On the x-axis, you can see the wave number. On the y-axis, it is transmittance. The scale of transmittance is from 0 to 100, and the x-axis, it is from 4000 to 400. Here it is showing 500, but it is mid-IR is 4000 to 400. It is expressed in wave number. Then you must be wondering, what are the sharp peaks there? You know, each of these peaks corresponds to a particular absorption. I told you a complex molecule or even a molecule is made up of several bonds like CH, NH, OH, CO, alcoholic, carboxylic acid group, and they will be vibrating at the particular frequency. And you can see when we irradiate the sample with a radiation from 4000 to 400, some of these regions, see, you can see at 4000, it is 100% transmitted. So light is 100% transmitted, but at 4800, no, sorry, 3800, you can see a dip. That means in the compound, there is some bond which has a natural vibrational frequency at 3800. And then if you come a little more to the front, you can see another dip at 3000. That means there is another bond that is having a natural vibrational frequency at 3000. So 4000 to 400 range, some of the wavelengths, or in other words, wave numbers are absorbed by the sample. That is why we can see that there is a dip there. There is no 100% transmittance, but it is reduced. And you can see the intensity is not same for all the peaks. The intensity is different. You know what? Why it is different? Because the number of such specific bonds, maybe CH stretching is there, so many, like maybe 10, 15 CH bonds are there, then the intensity will be very high. Maybe the other one is concentration is very low, that bond will be limited, and that will give rise to a small dip or a small peak. And one more thing is very important, there should be a change in the dipole moment of the bond. So each chemically distinct molecule, if it is an acid or it is a chemical, whatever molecule it is, they will have a different absorption pattern. We can easily say no two compounds will have the same absorption pattern. As I told you before, it is like a fingerprint for a human. It is unique. That is the beauty of FTIR. So if you see a spectrum and we can say, okay, yeah, this is that compound. There is no question because it is 100% evidence that this is this compound because it is unique. And you saw how the spectrum looked like, percentage transmittance versus wave number. Then I told you, in order for a molecule to be IR active, this vibration should bring about a change in the dipole moment of the molecule. This is very important. If there is no change in the dipole moment of the molecule, there is no absorption or no IR activity will be shown. For example, HCl, we can see there is a dipole moment. It is a polar bond. So it will definitely show in an FTIR spectrum. But for certain bonds like H2, Cl2, we can see they are homonuclear diatomic molecules. They are IR inactive. Then we can find out how many possible vibrational modes are available for a molecule. We can take water molecule as an example. It's a simple molecule, H2O. The center is O and the other is H. We can see there is an equation. This is 3n minus 6 for a nonlinear. This is a nonlinear molecule. For a nonlinear molecule, the number of possible vibrational mode is 3n minus 6, where n is the number of atoms. Here there are 3 atoms, so it is 3 into 3 minus 6. There are 3 vibrational mode. If you look closely at the movement, you can see there is a symmetric stretch, asymmetric stretch, and bending mode. And each of these stretching or bending, or in commonly we can say the vibration, has that particular frequency. And in the third column, it is written they are all IR active. But when we come to the next molecule, this is a carbon dioxide molecule. It is a linear molecule. The equation is different. It is 3n minus 5. N is the number of atoms. So there are 4 vibrational modes possible for this carbon dioxide molecule. But we can see only 3 are IR active, because the first one, the symmetric stretch, it won't bring about a change in the dipole moment of a molecule. But this degenerate bend, these two are known as degenerate bend. This and the asymmetric stretch bring about a change in the dipole moment. So it will be recorded, or these are IR active. That frequency is also noted in the middle column. Now, we have seen for a molecule only this number of modes are there. Then why the spectrum is very complicated? It is not like 5 or 6 peaks. It is a complex spectrum, because as in the other previous slides, we have seen the number of vibrational modes, but these are not the only transitions there in the spectrum. The above discussed ones are fundamental absorption that I told you, from the ground state to the lowest excited energy state, V0 to V1. But there are chances of overtone, excitation from ground state to the higher energy levels, which are the multiples of the fundamental. Then there are combination bands. 2 vibrational frequencies in a molecule, sometimes they couple to give rise to a new frequency. Then there are different bands, which results from the difference between 2 interacting bands. Then there is another phenomenon called Fermi resonance. When a fundamental vibration, the one that I told you, V0 to V1, combines with an overtone or a combination band, this coupled vibration is called Fermi resonance. Now let's come to the instrumentation part. I told you there were dispersive infrared era in the beginning, and then came the Fourier transform. The dispersive infrared uses monochromator, prism or grating, and they used to separate the infrared light into separate wavelength, and then they pass them through the they use a separation. Separate wavelength was analyzed. We can see this was the old dispersive infrared machine. I'll show you this. See, in dispersive, it is a double beam design. 2 equivalent beams from the same source are passing through the sample and the reference chamber as independent beams. And then they are alternately focused on the detector by use of an optical chopper. You can see a mirror to separate them. So one will be reaching the detector at a time. Then you can see a diffraction grating. The purpose of the diffraction grating is to separate the wavelength of light, and it directs each wavelength individually through the slit to the detector. So in dispersive, one wavelength is measured at a time, not all, and the slit will control the spectral bandwidth also, and the grating will select the desired wavelength. For this, an external source of wavelength calibration was required because there was no precision laser. So it was the beginning, mid 1960s, they made this one. So it had several drawbacks. Low sensitivity was bad. Then came so this was the dispersive type. Then came the Fourier transform infrared spectrophotometer. Here, the working principle is different. The optics, mainly the optics is different. Here, the diffraction grating or prism was the core, but here it is another setup called the interferometer. This is the optical system diagram for an FTIR spectrophotometer. You can see there is a light source, and from the light source, multiple wavelength is emitted from an infrared source. Then they are collimated. Collimated means they are made parallel and they are introduced to an interferometer. The box thing, that optical setup is known as an interferometer. As you can see, interferometer is made up of, there is a beam splitter which splits the beam into two parts. One goes to the fixed mirror straight, one will be reflected to the moving mirror. You know why? This is used to modulate the wavelength from the broadband IR source. The IR source is giving a broad band of infrared radiation, but with the interferometer, they are making it's modulating the light source. What happens is that when the light is first incident on the beam splitter, you can see beam splitter, it is written there, it splits the beam into two parts. One will go to the fixed mirror and the other will go to the moving mirror. Then they will be reunited again, but when they reunite, as the name suggests, moving mirror is always moving. So it will produce a phase difference. This phase difference causes, it is like constructive interference and destructive interference. This reunion causes an interference pattern. It is a complicated signal which has, in addition to the normal range, we have constructed and destructed waves in that. That is known as an interferogram. So an interferogram will, I'll show you, light source, then it goes to the beam splitter, one goes to the moving mirror, then the other goes to the fixed mirror. They will reunite and then it goes to the sample chamber. After passing through the interferometer, the light is focused on the sample in the sample compartment. Here we can see all of them are going at the same time, not one by one. The optics is different. There we were using diffraction grating or prism to separate the wavelength. Here all the wavelength will be going at the same time to the sample chamber. See, and the light is focused on the sample and then it goes to the detector. The detected interferogram we cannot interpret easily because I will show you how an interferogram will look like. It is a complex signal. We cannot easily interpret it. And then at this point, it is subjected to a mathematical procedure. We know the term Fourier transform, FTIR. This is a mathematical procedure. It changes the interferogram into a proper spectrum, which we can analyze and which we can understand and read and interpret. And the final result, see, this will look like this. The first one is the interferogram, which is a plot of intensity against optical path difference. We will not understand any of this. And then it will, after subjecting it to a mathematical procedure, we can see the spectrum in a better understanding format. So interferogram, which is a function of time, and the time domain is changed into frequency domain, then it is deconvoluted to produce a spectrum. So the final result, this all happens inside the system. The final result that we get will look like the one I showed in the right-hand side, which can be easily interpreted. So this is about Michelson interferometer. I told you in 1880s Michelson developed this interferometer, and in FTIR, interferometer is the core, or we can say the heart of the spectrophotometer, but in the dispersive, it was the grating or prism. And let us see, this is what happens in an interferometer. Is really important thing in a spectrophotometer, in FTIR. Now, what are the advantages of FTIR over dispersive spectroscopy? Faster analysis. We can see in FTIR, many scans can be completed and combined on an FTIR in a shorter time. In dispersive, one wavelength at a time means we have to wait for a long time to complete the scan. But here it is a faster data collection. In 5-10 seconds, the scanning will be completed because all the wavelengths are scanned at the same time. Then the second advantage is higher sensitivity. The optical path is it is simple, so it gives a better signal to noise ratio. Then it has higher wave number accuracy. I think you have noted that. You can see a helium neon gas laser here in this picture. So this laser is used for calibration. This achieves precise wave number measurement. So the wave number accuracy is way better than the dispersive spectrophotometer. Then here we have a better resolution. We can clearly distinguish closely spaced peaks. Then the signal averaging multiple scans can be taken, and since there are no narrow slits, more energy pass, and which gives better signals. Now, some of the sources of IR that is not very important, like Nernst blower. These are the sources that are available. These are the pictures of the sources. Each has different temperature. Incandescent wire, mercury. Then these are the detectors, DTGS detector, MCT detector. Each has its own benefits or better performance. Now, the most important part is the sample preparation. In FTIR, we can analyze solid, liquid, and gaseous samples. For solid samples, we have a sample holder. Even films we can measure. We can use the film holder to hold the film. We can even analyze gaseous samples. I will come to that in the next slide. And for FTIR, various cells and windows. And one thing we have to keep in mind is for FTIR, we mostly use potassium bromide or sodium chloride cells and windows because they are transparent to FTIR. That is, there is no interaction from them. No, they are harmless. It won't show its present in the spectrum or anywhere. So mostly we use potassium bromide or NaCl in the optics in the windows and cells. But we can see in KBR the range is from 4000 to 400, but for NaCl it has a short limitation. We can see the range goes up to 650 only, not up to 400. So we always prefer KBR over NaCl. For solid samples, I'm sure you might have seen me grinding and making the pellet most of the time. So this is the most commonly used method for solid samples. We mix with solid with potassium bromide. Why potassium bromide? Because potassium bromide is transparent. We take, the ratio is very small. The sample only 1:100. Potassium bromide should be like way higher than sample. A small amount of sample is taken and it's finely mixed with potassium bromide with pestle and mortar. Then grind it into a homogeneous mixture. Most important, we have to make it into fine powder. Otherwise, the scattering effect will be there. And when we make the pellet, it should be transparent. Otherwise, if it is too cloudy, you won't get a better result. So this is the die that we use on the left side. It is 13 mm die, 10 mm die. The diameter, it is the diameter of the pellet. And the right side is the pellet press. You can see 3 to 7 tons of pressure is applied. It is automatic. Sometimes we have to use the manual one, but this much pressure is applied to make the thin transparent pellet. The thickness of the pellet is important because according to Beer-Lambert's law, we know absorption is directly proportional to path length. In a pellet, the path length is the thickness of the sample. And the concentration is like how much sample we put. And most importantly, it should be transparent. And KBR has a disadvantage, like it is hygroscopic. It absorbs moisture easily. So it should be kept in the desiccator and it should be made really fast and presented into the sample compartment. We cannot wait for a long time after making the pellet. This is one method for solid samples. Next is the Nujol mold. This is a liquid paraffin. We can mix the sample with this Nujol, which is a liquid paraffin, and make it into a thick suspension or a paste. And you can see in these two discs, right, flat salt plates. We can spread a thin layer on one of this and sandwich with the other one and press it properly. And this can be present to the sample compartment. So this is the second option. First one is KBR pellet. Second is the Nujol mold for solid samples. Next is the thin solid film method. We can use some solvents like chloroform, carbon tetrachloride in FTIR. They don't have any interference with the spectra. So we dissolve the solid samples in those solvent, mostly chloroform, and dissolve it properly. Then we take a thin film on a KBR disc. In the first picture, we can see the sample is not enough. Concentration is not enough, so you won't get a good IR spectra. In the second one, we can see it is too much sample. It is crusty. It is concentration is very high. Here also, we cannot get a good spectra. The third one is just right. See, the concentration is enough, and this is the third method for solid samples. So first KBR, then Nujol, then the thin solid film method for solid samples. Whatever solid sample, if it is soluble in chloroform, we can do it like this. Next is for liquid samples. If it is a neat liquid means that one that is not mixed with any other solvent. If it is a neat liquid, this can be examined between two salt plates, KBR or NaCl. Put 1 or 2 drops on one plate and sandwich. With the capillary action, it will hold tight, and this pressing will produce maybe 0.01 millimeter or thin layer. Then they are presented into the sample compartment. Then we have another option for liquid cell, which is demountable. Demountable means the parts that you see, we can disassemble and reassemble again. And there is a spacer here. This adjusts the thickness. There are different kinds of spacers available with different materials and different thickness. Polyethylene, mylar spacers, 0.04 millimeter. It's usually in the millimeter range. So if we feel the concentration is not high, we can increase the size of the spacer, and with the spacer, we can adjust the path length. Here we can demount or disassemble them and reassemble them. Another is the fixed cell. Here we can see the sealed cell assembly. This is fixed. And here there is a point where we can inject the sample and drain it from here. Personally, when I use this one, I find it very difficult to clean. The other one was better. Cleaning part and contamination also. This one is the sealed one. The thickness is fixed. We cannot change it. It is mostly used to measure volatile samples. The other one, if we press and close it, by the time we do it, it will be evaporated. But here for volatile samples, this fixed cell is better. We can easily inject it. Within seconds, we can scan and get the result. The other one requires some time. By the time it will be gone. And there is a stopper here, so it won't let the volatile sample evaporate. These are the options for liquid samples. And what if it is, as I told you, the KBR and this one, NaCl, they are hygroscopic, which these cells, they will melt in the water. If the sample contains water, there is another option, zinc selenide. This is not deliquescent, it is resistant to moisture. So the sample, if the sample has water content, we can use this zinc selenide cell for the analysis. Then for gaseous samples, we have the gas cell. The spectra of gases or low boiling point liquids. HCl also we can do in this one. Put some drops of HCl in this and close it tightly. The path length is important because this much space should be there, because it is not thick, it is gas, it will disperse, and the concentration may not be like that of a solid or a liquid. So we need little more path length for gaseous samples. This can be used for gases or low boiling liquids, which can be taken. It is an evacuated cell, and the windows should be transparent. Here also we can use sodium chloride, potassium bromide windows. They are available in a large size, like few centimeter to 40 meter is available. With this gas cell, we can analyze air pollution gases and industrial gases also. So these are the different methods for analyzing solid, liquid, and gaseous samples. Now, polystyrene is used as the standard for KBR, I mean FTIR. We are provided with a polystyrene film. We take the spectrum of a polystyrene film, and they have noted some important peaks like 2923. Here you can see 1600 and 1060, and we cross check with the result. If these peaks are there in the polystyrene standard, and their position is not changed, or the wave number accuracy is there, maybe plus or minus 0.1, 0.5 is acceptable. If it is there, we can say the instrument is in good condition. So this is the standard that is used for FTIR. Then you can see this region 4000 to 1500, this region, and then the second region is this. This FTIR spectrum is divided into two regions. The complex one, the crowded one, is known as the fingerprint region, the region from 1450 to 600. Because most of the absorption happens there and it is complex, the unique patterns are found. As I told you, here is the fingerprint. Like the unique patterns or the complex peak appear there. That is why it is called fingerprint region. But the starting from 4000 to 1500, most of the simple stretching vibrations happen here, NH, OH. So it is known as the group frequency region. Now, how we can interpret the FTIR spectrum? This is a correlation chart or the table. Here, by looking at the correlation chart or the table, this is available online. When you get a spectrum in your hand and you suspect the presence of such certain bonds, you can compare with this thing. Here, they have mentioned which all groups absorb at what all frequencies. For example, aromatic ring. In your spectrum, if you see a peak at 3000, between 3000 and 3150, we can say, and look at the intensity. If it is a medium, we can say it has an aromatic ring. Or if there is a peak between 3300 and 3500 and the strong and broad peak, it should be a broad peak, then we can say this is an alcohol. So this is used to study or interpret the spectrum. Correlation chart, it is available online. Anywhere you can access a correlation chart. And now, how to approach the analysis of an FTIR spectrum? We have to concentrate when we get for mostly for I am here I am showing mostly the organic compounds. So when you get a spectrum, first of all, you look for a carbonyl peak for an organic compound. See, a carbonyl stretching happens between 1600 and 1800. It is not a particular frequency. They always show a range because shift can happen, because whatever is surrounding the carbonyl group, this will affect the position of this peak. It won't be at exact 1700 position, because on the left side and the right side, or whatever is connected to the carbon atom, it will affect the position. So first of all, when you get a spectrum, you analyze whether, for organic samples, whether a carbonyl group is present. If there is a strong bond peak at this position, go for the next one. Check whether there is an OH peak there. This shows an OH peak. As in the correlation chart, it is a very broad peak. So if CO and OH is present, we can say it is an acid group. If COH is not there, go check the amide group, NH. If it is a strong absorption at 3400, similarly, we can find out esters, anhydrides, aldehydes, and if all the 5 groups are not present and only the CO is there, we can say it is a pure ketone. Similarly, if ketone is absent, you can find out whether it is alcohol, amines, ethers, aromatic, triple bond, whatever. Now, we have a FTIR library. FTIR library is a digital database of the infrared spectra. Here, they have a collection of reference IR spectra of known substance stored in a software. By comparing our spectra with the FTIR library, so what we do is we get a spectrum, then our spectrum, the software compares it with the thousands of, it is like referring a dictionary. We want to find a word, we go check the library, find a dictionary and find the word. Similarly, we got a spectrum, but we want to know what it is. We have a big, huge digital database of infrared spectra. By comparing the spectra with the digital database, we get an idea what our compound is. They will give a match or a similarity score. So you can identify the compound. There are several libraries for organic compounds, polymer libraries, pharmaceutical materials, environmental libraries, forensic, biochemical. Even they have some companies provide industrial or in-house laboratories. They are specialized database. And then there are commercial large database where millions of FTIR spectra are recorded. We can easily find out with the help of that one. Then let's come to the main point. What are the applications of infrared analysis? It is mind-blowing. They can be used in several fields and it is interesting also. I'll go one by one. Pharmaceutical, forensic, polymer analysis, food research, quality assurance, environmental, biochemical, coatings and surfactants. Okay, in pharmaceutical research, first one is we can identify the drug. It is called drug fingerprinting. What drug is it? Whether it is like pure drug, we can do the quality control of raw materials. Then quantitative analysis, the drug concentration we can find out. And we can even detect the counterfeit drugs, whether there is anything wrong with this we can find out with the FTIR spectroscopy. Then in the field of forensic science, it is even more interesting. We can identify the unknown substance, what drug it is, what is it, what narcotics, whether it is a poison, and we can find out the chemicals that are found at the crime scene. Drug analysis, which like we know several kinds of drugs, what kind of drug it is, a cocaine or a heroin, we can find out what kind of drug it is. Then paint and polymer analysis, that can be used in the case of hit and run case. With the paint analysis, sometimes they hit and run, we can find out the paint and we can match it with the this thing and find out. And explosives, residues like TNT. Then document examination. Sometimes people do false documents, right? With like fake signature or false bill they will make. We can analyze the ink, the paper, and find out whether it's a proper document. Then we can do biological sample analysis like blood stain, body fluids, saliva. We can use this FTIR spectroscopy for this one. Then toxicity. They detect toxic substances in the samples like cyanide. In forensic science, this is less common than DNA. Okay, we have the DNA test available, but it is very supportive in the field of forensic science. Then polymer analysis. What first one is the identification of polymers. When you get a polymer, with the help of FTIR spectroscopy, we can identify what kind of polymer is it. Because if it has a strong CH stretching vibration, we can say it is a polyethylene. If it has a strong absorption for CCl bond, we can say it is polyvinyl chloride. And if aromatic ring is there, we can say it is polystyrene. Then we can use it in the functional group analysis. As I told you, OH, CO, all the functional groups in the polymer we can analyze. Quality control. We can ensure the consistency of the polymer batches. If there is any contamination or wrong material is mixed, with the help of FTIR, we can ensure the quality or consistency of the polymers. Then additives and filler detection. Plasticizers, stabilizers, antioxidants, whatever is added to the polymer, we can detect its presence, and it is very important for industrial formulation. Then polymer degradation studies, how the polymer changes with heat, UV light, oxidation. It is also very important. Then polymer composition, it determines the ratio of different monomers, then crystallinity and structure. Then food research, food composition analysis. We know food is made up of, food has carbohydrates, proteins, lipids, carbohydrates, fats, proteins, that also we can analyze. Then the quality of the food we can detect, detection of food adulteration. Sometimes they mix cheap oil with the olive oil or mix sugar syrup with honey. Then the moisture content determination, how much percentage is there. It can prevent spoilage. Then analysis of fats, the unsaturated, that we can find out. These are the applications in food research. Then air, environmental and water quality, air pollution monitoring, soil contamination, pesticide is there in the soil, monitoring industrial wastage, the like in the river or seawater, we can find out whether the petroleum is mixed or not, water quality analysis. Then biochemical and biomedical research, we can use protein structure analysis. We need an additional software to understand this, but sometimes we can do to understand the secondary structure like alpha helix, beta complex, then lipid analysis, carbohydrate identification, whether it is a glucose or fructose or sucrose, DNA, nucleic acid, even disease diagnosis also is possible with FTIR, because the tissue, with the human tissue, we can see what all biochemical changes happen in the tissue or a fluid of a person. It helps in the early detection of cancer, diabetes, infectious diseases and all. So the possibility or the uses is unlimited, even coatings, surfactants. Now let's see what are the accessories for FTIR available. ATR is one of the easiest method. Attenuated total reflectance is one of the easiest method in FTIR spectroscopy. In this one, there is no sample preparation needed. Here we are using this setup. You can see on the top there is a crystal. That could be diamond, germanium or zinc selenide. We spread the sample on the top of this crystal, and you know what happens? The infrared beam will hit the crystal from the bottom. It undergoes multiple internal reflection at the surface of the crystal where it comes into contact with the sample, and it will penetrate into the sample at this point again and again, and then it goes to the detector. This sample is in contact with the wave. This wave is called an evanescent wave, which is a weak wave. So it is slowed down and there will be a penetration. Just keep in mind the penetration depth. So it will go into this, not fully, a little on the surface. It is a surface study. And then it will go to the detector. Few things that is to be kept in mind. It is very easy to use. Just spread the sample on the top of the crystal and done. It's quick analysis. But some of the points that is to be kept in mind is the refractive index of the crystal. It should be greater than the sample. And the close contact between the sample and the crystal is very important. If there is a gap or air bubble or the close contact is not maintained, the result won't be that good and the intensity won't be nice. So there are different types of crystals. Each has its own properties. Germanium, the highest refractive index. Their wave number is this one. Zinc selenide, low cost. The wavelength is very large. Diamond, but mostly we use diamond because it is durable, chemically inert. It can be used for all types of substance, whether it is cream or paste or clothes, paper, fingerprint, saliva, blood, whatever, even rubber, tires, a piece of whatever is there, we can simply place it on the top and analyze. The advantage is ease of use. It is non-destructive, no sample preparation. Crystals can be interchanged. Large or thick samples can be handled. Small quantity we can analyze. And as I told you, the intimate contact is very important. Refractive index should be greater and the crystal should be really clean. Now, what are the applications? I told you these are the applications. Now, there is another option for FTIR microscope. It is a technique that combines FTIR with a microscope to analyze a very small area of the sample. With FTIR, we know with all the techniques that I told you, the solid, liquid or the gaseous, we cannot focus to one point. But the advantage of this microscope is that we put the sample and then we want to analyze a particular point in the sample. We can focus the IR beam onto that point and take the spectrum of that particular point. It is really, really useful. But unfortunately, we don't have the microscope with us. We can do the chemical mapping. So chemical mapping, it creates, okay, so we got a substance and it is kept under the microscope. We focus the FTIR on that particular region. It creates a map which shows where the different chemicals are located. It is just like a map. It creates a map of the compound. The different colors represent the different functional groups or materials. It is really very useful for analyzing or finding out certain areas of the sample. Then in microplastics, we can use microplastics study. They identify and maps different plastic particles in a sample. Then in biomedical, they can map proteins, lipids, carbohydrates in the tissues, and they are used in cancer and pathological studies. And as I told you, there are different methods available, highly advanced techniques are available, but these are really supportive. Then material science, check the coating, multi-layer films, forensic science. We can visually see micron-sized sample. Now, another technique is TGIR, thermogravimetric infrared analysis. Here, we are coupling this thermogravimetric analyzer with the FTIR. It is a hyphenated analytical technique. In TGA, we can measure the mass loss on heating. By FTIR, we can identify the gases evolved during heating, like carbon monoxide, carbon dioxide, and water. What are the applications? In polymers, we can identify the decomposition products of plastics. We can detect carbon dioxide, the hydrocarbons from polymer breakdown. Then in pharmaceutical, we can study the drug stability on heating. We heat a drug and how stable it is, at what temperature, what all changes happen. It is the thermogravimetric study combined with the study of the evolved substances. Ideally, it is like two in one shot. By thermogravimetric analysis, we get the thermal stability of the sample. When it is coupled with FTIR, we can study the byproducts or whatever gases are evolved. In environmental analysis, it is very useful. It monitors the pollutant gases released during combustion, like carbon monoxide, oxides of nitrogen. Then helps in material characterization, understand the thermal stability. Petrochemical industry, which studies fuels, oils, lubricants. Then decomposition mechanism. It shows the step-by-step breakdown of materials, intermediate stage, starting, and the end, and the final gaseous products. So the applications are really good. This is the advanced techniques. Yes. Done. I hope you understood and it was clear.
I actually have a question real quick, if possible.
Yes, well,
Which one?
Uh, could you please provide us with the PowerPoint slides and the recordings, because it's kind of part of our final examination. So
Yeah,
that
sure.
would actually be great.
Yeah, but let me check with my boss and I will let you know. I hope it is okay to share. Okay?
sorry.
Okay, I actually just provided my email in the chat, so if possible, please send the slides. Thank you very much.
Okay.
Thank you.
Okay, sure.
Thank you, Shobha, for this wonderful and very informative presentation. Anybody else is having any questions?
I just want to say thank you very much. It's been really informative, actually, and we benefited a lot.
Thank you.
If no one is having any question, then we can wind up the session. Thank you, Shobha. Hopefully, maybe we have already started recording the presentation, and maybe we can share it to you all once it is done. We thank you all.
Okay, thank you.
Thank you.